we're going to hear from Dr. Annette Evans. Annette is an ORISE postdoctoral fellow at the USGS Northeast Climate Adaptation Science Center and the University of Massachusetts. Her work focuses on the effects of climate change on the risk posed by invasive species across the United States. She's currently working on synthesizing management priorities identified by land managers across the US as part of the Regional Invasive Species and Climate Change, or RISC, management networks. Annette is particularly interested in the eco-evolutionary cascades caused by the introduction or removal of invasive species from native communities. All right, everything looks good, Annette, so you are good to go.
Brilliant, thanks so much. I'm really excited to be here this afternoon to talk through one of the new tools that's been added to EDDMapS recently that some of you might have noticed, and to give you a little bit of background to where this tool came from. So this tool is called the Future Abundance Habitat tool, and it's based on some recent abundance models that I've been working on as part of my postdoc. And so for those of you that use EDDMapS quite frequently, it's located under this distribution maps tab. And so you'll notice that there are a handful of species where this new abundance habitat, future abundance habitat tab has been added. And so this is what I'm going to sort of dig into a little bit later on in the talk. But just to start off with, I want to give you some background into how we developed this tool and the data that went into that. So this tool builds on other EDDMapS tools that can be used for proactive management of invasive species when we're thinking about how climate change is likely to be impacting those invasive species. And I'm sure many of you are aware one of the ways that climate can impact invasive species is by species shifting their ranges. And it's these range shifting taxa that this tool is particularly targeted towards. And the view is that if we're able to identify which species are likely to be moving their ranges and where they're likely to be moving to, we can target those particular taxa to either prevent those species establishing in new areas in the first place, or if they are already there, we can seek to eradicate them early on before they reach higher, much larger populations. And so previous work by Jenica Allen and Bethany Bradley is targeted and sort of worked towards this prioritization framework that's already incorporated into EDDMapS. So everything I'm talking about today is all about invasive plants. So we're back in the world of plants. And so in 2016, Jenica and Bethany went and collected data on 869 invasive plants by pulling data sets from online data sources like EDDMapS. And for those nearly 900 species, they ran species distribution models using 13 different climate model scenarios. And the output of that work was to create species distribution models for these invasive plant taxa, and to create occurrence maps of where these species are likely to be in the future. And it's this data that's already been incorporated into EDDMapS through a tool called the Invasive Range Expanders Listing tool. And I'll show you what that looks like in a little bit. But one of the other important outcomes from Jenica's work was if you compile all of those output maps for those nearly 900 species that they worked through, you can stack them on top of each other to look for hotspots, so regions that are likely to support a large number of invasive species in the future. And so on the screen, I'm showing you one of those resulting maps that shows you those hotspot regions just for the north and northeastern United States. So the darker the red color, the higher the number of invasive plants that are likely to be able to establish populations in these regions with climate change. And you can see that there are some places on this map where up to 100 new invasive plants are likely to establish in climate change. And so while that's really helpful to have this list of 100 potential plants for these regions, that's a lot of species. And a lot of these species will be needing to be managed on top of species that are already there. And so this kind of led our group to ask, well, is there a way we can prioritize species even further than just identifying which are the ones that are likely to be shifting their ranges? And so one way that we could narrow down this list is to not just look at where a species could occur on the landscape, but also look at whether they can reach high abundance. And there's a couple of reasons for this. So one, there's not a perfect overlap in terms of habitat where a species can occur versus where they can become abundant. So on the screen, you can see two maps for two different invasive species that show you the overlap in this occurrence versus abundance range. So the yellow areas of the map are simply where a species can occur, but not reach high abundance, or at least we haven't recorded high abundant populations. Whereas those sort of darker blue colors are where a species can not only just occur, but also reach high abundance. And so you can see that that range of where they both overlap in occurrence and abundance is much narrower. So this is one way that we could try to narrow down that prioritization list. The second reason we might be interested in looking at where species could become abundant is because high abundance is also often correlated with higher impact. And for those of you that are out in the field managing, I'm sure you can also reconcile the fact that, in removing one individual or a handful of individuals from a landscape is much easier than trying to eradicate an enormous large population. And so for those reasons, we were looking at, figuring out, okay, well, which species are likely to become abundant with climate change and where? Are they likely to be shifting their ranges, and how are those ranges likely to be shifting? So to do that, we gathered abundance data, which whenever I talk about abundance here, I'm talking about some kind of metric of percent cover. And we used a cutoff of 5% to determine if a species was abundant or not. And so we gathered abundance data from 18 different online databases, including EDDMapS. And after going through a variety of data curation processes, we selected 144 species that are already established in the United States and have an East Coast distribution, because that was sort of our starting point for this research. And so for each of those 144 species, we did species distribution modeling, and we used a current suite of climate variables to estimate, what's our sort of status quo, where are species distributed currently, and then used a future climate scenario of 2 degrees of warming, which we expected to reach around 2100. And so we did all this modeling with some colleagues at the USGS using software called VizTrails. And I'm not going to get into the details of that modeling, but I'm happy to talk to anybody who's interested offline. But I will just jump straight into those results. So what we did is for each of those 144 species, we stacked the output maps on top of each other to look at abundance hotspots. So where are areas on the landscape that can support a large number of species that can reach high abundance? And so again, on this map, the darker the red color, the greater the number of species that can reach high abundance. And there's sort of 3 general regions in the eastern United States where we see these hotspots. So one's down northeastern coast of Florida and Georgia, and then the rest are just broadly distributed in the northeastern United States, in the Great Lakes region and Mid-Atlantic region. And all of these places can support abundant populations of over 40 invasive plant species. And so this is kind of our status quo situation. And so now we're interested to compare how climate change is likely to shift these hotspot locations. And so now this new map that I've just propagated here on the right shows you that with 2 degrees of climate change, the ranges of abundance habitat for these species are likely to be shifting northward, which I'm sure many of you are not surprised to hear, but also predominantly shifting towards the northeast, followed by the northwest. And so you can see that we still have quite a few regions where up to more than 40 species of invasive plant are able to reach high abundance. And now these are much more concentrated towards the New England region. In addition to this sort of broad overview, we can also dig in a little bit more on individual species and regional based trends. And so at a 4x4 kilometer scale, which was the scale of our study, we see evidence of regions maintaining invaders. So on average, if you look at this middle figure, 18 species that currently have abundance habitat in a particular region are likely to still be able to have abundant populations in the future. But interestingly, we also saw shifts in that species composition. So on average, a region is expected to gain 4 brand new invasive plant species, so species that can't currently sustain abundant populations, but will be able to in the future. And conversely, on average, regions are likely to lose up to 5, on average, 5 species. So there is evidence that climate change is likely to cause some invasive plants to struggle to maintain abundant populations. And that's kind of exciting in terms of a restoration approach, that maybe we can be redirecting some conservation money away from species that are losing habitat. And as I mentioned, we also have this breakdown based on individual taxa. So I mentioned that we've run these models for 144 species. And for each of those species, we've got output maps, kind of like I'm showing you here. So these are just two examples of two different species that show very different trends in terms of their responses to future climate change. So on the left, I've got wine raspberry, and wine raspberry is expected to experience an overall expansion of its abundance range. So in both these figures, the blue areas of the map are areas where the species currently is able to sustain abundant populations, but with climate change, its models suggest that that region is likely to become unsuitable. Whereas purple areas, the species are currently observed in high abundance and are likely to be able to persist into the future. And red areas are areas where species currently struggle to maintain high abundance or are not being reported in high abundance. And that area is likely to become suitable with climate change. And so you can see for wine raspberry, although there's quite a large area out west where we see this decrease in suitability, we see quite a large area of the species' current range in purple is being maintained and a large area is being gained. And then you kind of see the flip side for alligator weed, where quite a large extent of the current range is predicted to be unsuitable for abundant populations into the future. And so this kind of brings me into this new range expanders listing tool feature that we've been creating based on the output from the models that I've just shared with you. And so before I dig into what's new, I want to do a very brief overview of what's currently there. And so for those who are unaware, this invasive range expanders listing tool, which is a real mouthful to say, is located under this tools and training bar and under this database tools. And this again was developed originally based on the model results of the species models run by Jenica Allen. So those models were based purely on occurrence data. So was the species observed there? Yes, no. So when you click on the range expander tool, you get taken to a page that looks something like this. And so on this page, you can select what state you're focusing your work in. If there's a particular county that you're interested in looking at, or all counties, you can refine the list based on the degree of area. Do you just want to see what species are in that state, or are you more interested in a regional approach? And then the last drop-down menu that you see on the screen is choose number of models. And so just like our study, Jenica ran a variety of different models, and I think it was 13 different climate models. And so the higher the number of models, the greater the agreement in terms of the output values, that region is likely to be suitable for that species. So if you choose 13, it means 13 out of 13 models say, yeah, that region is likely to be able to support that particular species. And so as you toggle through these different drop-down menus, you can see a map propagating down here on the lower left that shows you the region that the data is being pulled from, and then a list of species, kind of like a watch list, is dynamically updates for you. And this kind of gives you a list of species that are likely to occur in that particular region or area that you've outlined with climate change. And so in addition to this very broad overview, you could click on one of these individual taxa and you could be taken to a taxa-specific page. And so in addition to information about the species itself and the records, you can see if you click on this counties button, you've got a variety of drop-down options. And the two based on Jenica's work are this future range, which I'm actually not going to show you today, and this future certainty. And so the future certainty shows you the breakdown in terms of model agreement. So how many models agree that that particular county in this stage is suitable for that particular species to occur. So again, the darker the green colors, the more models agree that that species is likely to occur there with climate change. And it's this future certainty map that we've now duplicated based on the abundance data. So this example on the screen I'm showing you is Japanese knotweed. And so here are all the different counties in the sort of geographic location where Japanese knotweed is likely to be able to occur with climate change. Oh yeah, now if you click on this future abundance habitat map, this is what that equivalent looks like for the abundance data. So again, we're still on Japanese knotweed, And again, still the darker the green color, the higher the number of models, and in this case, it's 15 models, agree that that region or that county is likely to be able to support abundant populations given climate change. And so the hope is that, if you're, looking to try to narrow down that list of species that you're either monitoring for or trying to manage in your particular state or county, you can not only look at if that species is likely to be able to occur there in the future, but also whether it's likely to maintain abundant populations. And so currently these maps are available for you to use on EDDMapS for 144 different species. And we do have a West Coast companion paper that we're developing. So most of the species, or in fact, all of those 144 species, have at least some abundance record east of around the middle of Texas line. And so now we've run the same models based on West Coast taxa. So for all of you that are working out west, that data, we're currently working on getting it uploaded to EDDMapS. And so you should have that available for an additional, 120 to 150 taxa. And the results for both the East and West are currently being written up. And so there will be a manuscript coming out. So keep an eye out if you want to learn a little bit more about the methods that went into sort of all the background analysis that generated these maps. And so with that, I just want to thank first all my co-authors, as well as everybody else who made all this work possible and our funding sources. And if I have time, I'll take questions. Otherwise, I will be here until the end. So happy to wait as well.
Thanks, Annette. That was fantastic. It looks like we already have a question here. Are there any cons of choosing to use multiple models? Are the models ranked somehow so that if you choose to use one, it picks a certain one for a reason?
Yeah, that's a good question. So we have in the tool, it doesn't tell you which model has suggested that this is a suitable region or a not suitable region. It depends on how conservative you want to be with your estimates. So if only one model out of 15 suggests that a particular region is likely to support an abundant population, it seems like there's quite a lot of error in there and a much greater level of uncertainty than if all 15 models say, yeah, this region is likely to be able to support abundant populations. So my advice would be, skew towards the higher agreement, but just know, if you want the most conservative list of species or estimate of that future abundance range, the higher the number of models, the more conservative that estimate.
All right, awesome. We had one more question come in. Are you using EDDMapS data to validate or ground truth your models as time goes on?
Oh, that'd be great. There is no current plan to do that, in part because I'm on a short-term contract. But yeah, that'd be really cool in the future, though. I'm sure that will happen. There was some model validation and checking during the model development process, but that was sort of, here's our pool of data and you develop your models on a subset of that data and then test it on the part that you didn't use to develop the models, not sort of based on real world application. But yeah, that'd be great going forward. But yeah, no current plans at the moment.
Right, sounds good. Well, if anybody else has any more questions for Annette, feel free to add those in the Q&A, but I think